students, welcome to Interconnecting Physics. Today I will teach you about electric potential and electric potential difference, in which we will be studying about units of electric potential due to a point charge, superposition principle of electric potentials, electric potential due to continuous distribution of charge, and electric potential due to a dipole. So without wasting time, let's get started. For regular updates, you can follow me on given links. So you see here, we have already finished the first chapter of class 12 physics, that is electric charges and fields. Today, we are going to start the second chapter, that is electrostatic potential and capacitance. These are the topics which are to be covered in this chapter. But since chapter is very lengthy, so we will cover only few topics of this chapter today. So let's start. So what is electrostatic potential energy? Before studying electric potential, we should know about electrostatic potential energy. So let us consider we have a charge plus Q, which is a source charge, and we have a test charge Q naught, which is very small as compared to this source charge. Means Q naught has very less magnitude as compared to this source charge. Now this charge is positive and Q naught is also positive. So due to electrostatic force of repulsion, the plus Q charge, that is source charge, will repel this test charge in the direction of electric field. Means this Q naught will move away from the source charge plus Q, that is in the direction of electric field vector E, that is along positive x-axis. But what is the new thing which we have to do here is we have to bring this test charge close to plus Q charge. That is, we have to bring this test charge Q naught towards this source charge. Now, you know, due to electrostatic force of repulsion, this charge is moving away from this source charge, but we have to apply some opposite external force to overcome that electrostatic force of repulsion. And that external force which we have to apply to bring this Q naught charge, this test charge, toward this source charge, we have to do some work. And that work done will be stored as potential energy of this test charge. Again I repeat, due to electrostatic force of repulsion, there is repelling force between plus Q and Q naught charge. So Q naught will move away from this plus Q charge, that is along positive x-axis, that is in the direction of electric field E vector. But we have to bring this Q naught charge towards this source charge. So we have to do some work, and that work will be stored as potential energy of this test charge. So let's start. Let us consider a positive test charge Q naught is placed at A in the electric field of another positive source charge Q. The force acting on the test charge Q naught in the electric field E vector is given by F E vector equal to Q naught E vector. This force will tend to move the test charge in the direction of electric field E vector. But the main point lies here. We have to move this positive test charge towards Q. Let F naught is the force acting on the test charge Q naught towards the charge Q. If the test charge is displaced through a distance dr vector, you see here dr vector, from point A to point B in the electric field E, then work done by external force is. Now, some points to be remembered here. Number 1, this charge Q naught should be displaced toward the source charge by very small steps. That is without acceleration. means there should be no change in the kinetic energy of test charge. Means this charge is displaced in infinitely small steps so that there is no change in acceleration and there should be no change in kinetic energy of the test charge. So small work done in bringing Q naught from point A to B will be dW A to B, which is equal to F naught external force dot small displacement, that is dr. Now the total work done from point A to B will be integration of A to B F naught dot dr vector. Now this F naught, this external force, is opposite to this electrostatic force of repulsion. So it means it is negative of Fe. If Fe is Q naught E vector, then F naught vector will be minus Q naught E vector. So work done, put the value of F naught here, that is minus Q naught E dot dr. Q naught can be taken outside from the integration. So this is the work done which is used in bringing the charge Q naught from point A to point B near the source charge. So this work done gives the difference in electric potential energy of the test charge between points A and B in the electric field. Okay, WAB is difference in the electric potential energy. Why difference? Because we have 2 points. If the electrostatic potential energy of test charge at point is UA and electrostatic potential energy of test charge at point is UB. So we have 2 points and we are doing, what are we doing? We are bringing this Q naught from A to B through very small displacements, that is dr vector. So this work done will be stored as difference in electric potential energy of the test charge between points A and B, that is UB minus UA in the electric field. So the difference in electric potential energy between the 2 points A and B in the electric field is the work done in moving a test charge without acceleration from point A to B in the electric field of source charge. Okay. Now let us assume this point A is at infinity. Okay. And there will be no electrostatic force between charge Q and test charge Q naught, because this point, this Q naught now is at infinity and we don't know where infinity is, where infinity lies. So it means there will be no force of repulsion between plus Q and Q naught. So we say that at point B, the electrostatic potential energy is UB, but at point A, which is now at infinity, means UA now is U infinity, and at infinity the electrostatic potential energy of test charge is 0. It means UB minus U infinity now. UB minus U infinity will be UB only, because the electrostatic potential energy of test charge at infinity is 0. So W infinity B, because A is being converted into infinity, minus Q naught integration from infinity to B E dot dr. So this is the electric potential energy at one point, electric potential energy, and earlier it was difference in electric potential energy. Okay. So definition: electric potential energy of a charge at a point in the electric field of any charge. At a point of a charge means test charge Q naught, and at a point in the electric field of any charge means source charge, that is plus Q, is defined as the work done in moving a test charge from infinity to a point in the electric field. To a point means at point B. If we are bringing this Q naught from infinity to point B, then that point is here B. Okay. So it is the work done. What is electric potential energy? It is the work done in moving a test charge Q0 from infinity to that point in the electric field. Instead of test charge, we can also write unit positive charge. Unit positive charge. That is plus 1. Then we say electric potential energy of charge at a point in the electric field of any charge is defined as the work done in moving unit positive test charge from infinity to that point in the electric field. Now, some important points. This integration from A to B E dot dr is called line integral of electric field intensity between points A and B. It is the line integral of electric field intensity. Now, number 2. Since the work done by electrostatic force, this work done by electrostatic force acting on a charge only depends upon initial and final position, only depending upon initial and final point A and point B, and it does not depend upon the path followed by the charge particle. Okay. Therefore, the electrostatic force and electrostatic field are conservative in nature. In chapter 1, I told you that electrostatic force, that is coulomb force, is conservative in nature. Coulomb force. Okay. Then I told you there that in second chapter I will tell you what is conservative force. So the definition of conservative force is if the work done by conservative force acting on a charge only depends upon initial and final position of the charge particle and does not depend upon the path followed by the charge particle, then such force is called conservative force. Okay. Number 3. Work done by conservative force over a closed path is always 0. Okay, I explain this with some examples. Suppose I have some closed path here, A to B and B to A, because it is closed. If we are starting our work done from A, then we have to end up our work done at point A. So from A to B, what will be the work done? WAB equal to minus Q naught. If we have to move test charge Q naught from A to B, then what will be the work done? Minus Q naught A to B E dot dr. Okay. And from B to A, the work done will be WBA equal to minus Q naught from B to A E dot dr. Now total work done will be W equal to WAB plus WBA. Put the value WAB, which is minus Q naught A to B E dot dr. And what is BA? It is minus Q naught B to A. If we inverse this integration, means limits is B to A. If we do this from A to B, then it will be minus and minus minus will be plus. That is Q naught A to B E dot dr. Then it will be cancelled out and total work done will be 0. So means work done by conservative force over a closed path is always 0. Now let's start with electrostatic potential difference. The main point of this chapter, that is electrostatic potential difference. Potential difference. Now always remember, potential difference is the basic quantity, potential difference is the main quantity. Okay. Potential is not the basic quantity. Potential is not the basic quantity. Potential difference is the important and basic quantity. Okay. And to know the potential difference, to calculate the potential difference, we should have some points. Number 1, there should be at least 2 points in the space. There should be at least 2 points in the space. Okay, there should be 2 points in the space, and that space may be free space or any medium. Okay. Number 2, there should be electric field present over that surface. Okay, there should be electric field present over that space. Okay. So let us consider UA is the potential energy of the test charge Q naught at point A, and UB is the potential energy of the test charge at point B. So we already know what is work done from A to B in bringing the charge from point A to B is UB minus U. That is delta U, means change in potential energy difference. Okay. Now, what is electric potential difference? Electric potential difference is UB minus UA divided by Q naught. If we divide this electrostatic potential energy difference with Q naught, that is test charge, it will become WAB divided by Q naught, and this quantity will become delta V, that is electrostatic potential difference. This delta means difference, or it can be written as, it can be called as electric potential energy difference per unit charge, or in simple language we can say that work done divided by charge. So UB, we know that UB minus UA is minus Q naught integration from A to B E dot dr. So when we divide this with Q naught, this Q naught cancels out with Q naught, and we are left with minus A to B integration E dot dr. So this is electric potential difference. Okay. Now definition, potential difference between any 2 points. Again 2 points, one is A, one is B, because the Q naught charge is being moved from point A to point B. So potential energy between 2 points in electric field is the, what is this? It is the work done in moving a positive test charge from one point to another point against the electrostatic force of the electric field, but does not depend upon the path followed. Or in simple language, we can say that potential difference between 2 points in an electric field is the electrostatic potential energy difference per unit charge. Electrostatic potential energy difference per unit charge, or work done in bringing the charge from point A to B divided by test charge. Okay. Now, what is electric potential? What is electric potential? Again, let us consider point A is at infinity. Okay. So, let U be is the electrostatic potential energy of the test charge at point B, and UA is the electrostatic potential energy of the test charge at point A. Let us consider point A is at infinity. Now then potential energy UA at infinity will be 0, because we don't know where is infinity. Okay. So UA, if A is infinity, then U infinity will be 0, means electrostatic potential energy of test charge Q naught at infinity is 0. So UB minus U infinity will become UB, because U infinity is 0, and simply we can write it as U, that is electric potential energy. Okay. Now electric potential at point B now given as V equal to U divided by Q naught, that is work done divided by charge. So simply electric potential we called as work done per unit charge, work done per unit charge. You always remember work done per unit charge. So you know U equal to minus Q naught infinity to B E dot dr. So if we divide this equation by Q naught cancels out with Q naught, and we are left with electric potential capital V. It is denoted by capital V, which is minus integration from infinity, because the point is infinity, and the point where we have to bring this charge is point B, E dot dr. So electric potential at a point in the electric, at a point, because we have only one point. We don't know where is infinity. Okay. So electric potential at point in the electric field is defined as the work done in moving a positive test charge from infinity to that point in the electric field of source charge. Or in simple language, it is the work done per unit charge. Okay. Now, units of electrostatic potential and electrostatic potential difference means units of V and delta V. Units are same. Okay. We know electric potential is U divided by Q naught, means W divided by Q naught. So SI unit of electric potential is volt and symbolized as capital V. Okay, so 1 volt is W is measured in joule and Q naught is measured in coulomb. So 1 volt equal to 1 joule divided by 1 coulomb, that is 1 joule coulomb inverse. So we have to define 1 volt. Whenever we have to define 1 volt, what we do, we make joule and coulomb as 1 unit. Okay, so electric potential at a point in the electric field is said to be 1 volt if 1 joule work is done in moving 1 coulomb of charge from infinity to that point in the electric field. Okay, now CGS unit of electrostatic potential is stat volt. So 1 stat volt will be, what is the CGS unit of work? Erg. What is the CGS unit of charge? Stat coulomb. So it is 1 erg divided by 1 stat coulomb. Therefore, electric potential at point P in the electric field is said to be 1 stat volt if 1 erg of work is done in moving a 1 stat coulomb charge from infinity to a point in the electric field. Now, what is the relation between SI unit of potential and CGS unit of potential, that is volt and stat volt? So 1 volt is 1 joule divided by 1 coulomb. 1 joule is 10 raised to power 7 erg and 1 coulomb is 3 into 10 raised to power 9 stat coulomb. By calculating this, we will get 1 by 300. So 1 volt is 1 by 300 stat volt. Now, dimension formula for electrostatic potential. We know potential is work done divided by charge. So what is the dimension formula for work done? It is mL2 T minus 2. And what is the dimension formula of charge? I have already told you in chapter 1 that dimension formula of charge is always AT. When we multiply and divide this, we will get mL2 and T here 1, T minus 3, A minus 1. Okay students, never cram the dimension formula. Always learn the formula and calculate the dimension formula from the given formula. Okay. Now electric potential is a scalar quantity. Electric potential is always a scalar quantity. Now the points to remember here, electric potential energy, that is U, depends upon the test charge and electric field. Depends upon the test charge and electric field due to the interaction between test charge and electric field. But the electric potential V is the characteristic only of the electric field and independent of the test charge. Okay, electric potential V only characteristic of electric field. It does not depend upon Q naught, that is test charge. But U depends upon both test charge and electric field. Okay. Now, electric potential due to a point charge or electric potential due to an isolated charge. So, let us say we have source charge plus Q and we have unit positive test charge, that is plus 1 at point P. Okay. And the distance between this source charge and point P is x. Now, we already know due to electrostatic force of repulsion, this charge plus Q, that is source charge, will repel plus 1 charge away from this source charge. Okay, it will move along positive x-axis or it will move in the direction of electric field. But we have to bring this unit positive test charge towards plus Q. So some work is to be done. Okay. So let us consider a point charge plus Q and a unit positive charge placed at point E in the electric field of source charge Q. Let the distance between plus Q and plus 1 is x. Now the electrostatic force of repulsion between two charges is given by Coulomb's law, which is 1 over 4 pi epsilon naught first charge multiplied by second charge. First charge is plus Q, second charge is plus 1 divided by distance between these two charges, that is x square. Okay. Now the direction of this force will be radially outward, that is in the direction of electric field, that is along positive x-axis. This force will repel the unit positive charge, but the main important point here. But we have to bring plus 1 charge towards the Q. Let unit positive test charge is displaced towards Q through a distance dx without acceleration, slowly so that kinetic energy does not change. Okay. Then small work done in moving plus 1 charge through displacement dx will be force into displacement. Now open up this, we will get f dx cos 180 degree. And what is the value of cos 180 degree? It is minus 1. So it is minus f dx. Okay. Now put the value of f here. What is f? 1 over 4 pi epsilon naught q over x square. Put the value here. Now the total work done in bringing this unit positive charge from infinity to point A. Let us say this point B is at infinity. Now the total work done from infinity to point A will be, suppose x equal to infinity first and then x equal to r at point A. You see here we have to bring this plus 1 charge at A, and at A the distance is small r. So we have to bring the test charge from x equal to infinity to x equal to r. Okay. The limits of integration will be, the limits of integration will be from infinity to r. Put the value of dw, take out the constant terms, common terms, q divided by 4 pi epsilon naught out from the integration. Now w will be integration of dw, which is equal to minus limits infinity to r, q divided by 4 pi epsilon naught x square dx. Now take the constant terms out of the integration, that is q over 4 pi epsilon naught, and integration of 1 over x square into dx. Let us calculate integration of 1 over x square dx, which is equal to x raised to power minus 2 dx. We know the formula for integration, that is x n dx equal to x n plus 1 x raised to power n plus 1 divided by n plus 1. And here n is minus 2. So x minus 2 plus 1 divided by minus 2 plus 1. So x minus 1 divided by minus 1, and answer is minus 1 over x. So substitute this value here. Now minus and minus will be plus. Put the upper limit 1 over r minus lower limit 1 over infinity. 1 over infinity is 0. So work done will be q divided by 4 pi epsilon naught r. So the amount of work done in bringing plus 1 charge from infinity to point A is equal to electric potential at point A. So therefore V is equal to 1 over 4 pi epsilon naught q divided by r. And you see V is inversely proportional to r. Okay. Now if charge q is positive, potential will be positive. If charge q is negative, potential will be negative. Okay. If charge q has a large value, potential will be large, and if charge q has small value, potential will be small. And the variation of electric potential with distance is V and R. For positive charge, the variation is like this. For negative charge, variation is like this. And the variation between V and 1 by R, because V is inversely proportional to R. We can also say V is directly proportional to 1 by R. Okay. If V is directly proportional to 1 by R, for positive charge graph is like this, and for negative charge graph is like this. Okay. Now electric potential due to single charge is spherically symmetric, because we have electric potential due to point charge is 1 over 4 pi epsilon naught q divided by r. Okay. It is depending only upon r. The point is here and r is here. So it means in this direction r is here, 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 in this direction r is here. So when we draw in 3 dimension, we will get a sphere. It means if r is constant, then the electric potential due to single charge is spherically symmetric. It has same value at all points on this sphere, because the value of potential is same at all points at a distance r around this charge. Okay. Now, electric potential energy due to group or system of point charges, that is principle of superposition of potentials. Okay. So for this, we have to calculate the net potential at O due to all the charges. So what is the definition? Principle of superposition of electric potential states the net electric potential at a point O, net electric potential at a point O at any point, or we can say due to discrete charges is given by algebraic sum of their individual potentials at that point. Means it will be V1, V2 plus V3 up to so on. This is the simple algebraic sum because potential is a scalar quantity. Okay. Now what is V1? V1 is the potential at point O due to Q1. V2 is the potential at point O due to Q2. V3 is the potential at point O due to Q3. Similarly, Vn is the potential at O due to Qn. And the formula we use here, 1 over 4 pi epsilon naught Q by R. So electric potential at point O due to Q1 will be 1 over 4 pi epsilon naught Q1 over R1. Electric potential at O due to Q2 will be V2 equal to 1 over 4 pi epsilon naught Q2 over R2, and due to Q3 it is Q3 over R3, and similarly up to so on Vn is equal to 1 over 4 pi epsilon naught Qn over Rn. Now according to principle of superposition, the net electric potential at O will be the sum of all these potentials. Okay. This is the OK relation for superposition principle, but if you want to convert this relation in summation form, then we can write 1 over 4 pi epsilon naught summation limit I from 1 to n and Qi, because Q1, Q2, Q3 value is changing, so we write it as Qi, and similarly for R, that is Ri. Okay. Now, electric potential due to group of charges, that is in terms of position vector. So let us consider coordinate system x, O, x, y, z, where we consider number of charges Q1, Q2, Q3 up to so on Qn. Why up to so on Qn? Because for our convenience, we take only few charges, because n here, n can be 1000, n can be 10,000, and can be more than this. Okay, but in single page it's very difficult to draw all the charges and calculate the individual potentials. It will be very complex situation. So for our convenience, we take few charges only and we generalize as Qn. Okay, so let us consider point P, where we have to calculate the net electric potential V due to all these charges. Let R1 vector, R2 vector, R3 vector, Rn vector are the position vectors of Q1, Q2, Q3, Qn respectively, and R0 vector is the position vector of the point P, where we have to calculate the net electric potential. Okay, so V1 equal to 1 over 4 pi epsilon naught Q1 over modulus of R0 minus Rn vector. If you want to have the knowledge about how to write potentials, electric fields, electric force in terms of position vectors, then click on I button. Know how to write equations in the position vectors. Okay. Now, electric potential at P due to Q2 will be 1 over 4 pi epsilon naught Q2 over R0 minus R2. Similarly for Q3, Q3 over R0 minus R3 modulus. And similarly for Qn, 1 over 4 pi epsilon naught Qn over R0 minus Rn vector. So net electric potential at P, we will add all the potential V1 plus V2 plus V3 up to so on plus Vn. Okay. And this is the final relation, but if you want to convert this relation into summation, then 1 over 4 pi epsilon naught is common in all, can be taken out from the summation, and the limit of summation is from I equal to 1 to n. Qi divided by R0 is same, so R0 is written as such minus Ri vector. Okay. Now, electric potential due to continuous charge distribution. Okay. What is continuous charge distribution? In chapter 1, I have told you in detail, but again I tell you what is continuous charge distribution. Number 1, continuous charge distribution is macroscopic system. Macroscopic system. Okay. Macroscopic system is the system which we can see with our naked eyes. Okay. And number 2, in macroscopic system means in continuous distribution of charge are very closely packed, very closely spaced. Okay, means they are packed so closely that we see the situation like this. We see continuous distribution. Means we don't know how many charges are present over here. 10 charges, 20 charges, 100 charges. No, we don't know how many charges are present over in the continuous distribution of the charge. So number 3, quantization principle, that is Q equal to NE, is failed here. Okay. So if we want to know how many charges are present over here, we take the help of charge densities, that is linear charge density, sigma charge density and volume charge densities. Suppose we take the example of linear charge distribution. It is continuous distribution of charge and we don't know how many charges are present over here, but we have to calculate the charges. So we take small length element, that is dl, and we write it as, let us say, suppose dq charge is present over here. So we take the help of lambda and we say dq over dl. Again we take next element, we say dq over dl. Okay, again next element, and then we calculate total charge by integration. Okay, similarly for surface charge distribution, we take small element and we calculate surface charge density dq over ds. Okay, so electric potential due to linear charge distribution is v equal to integration of dv. Okay, what is v? It is electric potential, because small potential will be here dv, small potential will be 1 over 4 pi epsilon naught dq. If dq is charge present over here, then we write dq over r. Then total potential will be integration of dv, which is 1 over 4 pi epsilon naught. Okay, what is dq? dq will be rho dv divided by r. Okay, if we take linear charge distribution, then dq will be lambda dl. If we take surface charge distribution, then potential will be in the term of sigma ds, because sigma equal to dq over ds. If we take volume charge distribution, then potential will be in the term of rho d. But if we are given with case in which all three types of distributions are present simultaneously, then we have to calculate the total potential of at point A due to all these distributions. What we do, we calculate first the separate value of potentials due to linear charge distribution, due to surface charge distribution, due to volume charge distribution, and we add up all these values and get the result. Okay. Now, electric potential due to electric dipole, very important. So for this, let us consider electric dipole. You know what is electric dipole? Electric dipole is the arrangement of equal and opposite charges separated by some distance. So let us say minus q charge is present at A, plus q charge is present at B, and they are separated by distance 2L. What is 2L? It is the dipole length. Dipole length. We divide this length as AO is L and second half OB is L. Let us consider point B where we wish to calculate the electric potential. Okay, let it is at distance r from the center of the dipole, and it is this line OB is making an angle theta with the direction of dipole moment. What is the direction of dipole moment? From minus q to plus q. Join AP, distance AP is r1, let us assume. Join BP and the distance BP is r2. Now, let us calculate the potential at point P due to minus q charge. It is V minus 1 over 4 pi epsilon naught minus q over r1. Because I have already told you, if charge is negative, potential will be negative. Potential at point P due to plus q charge is 1 over 4 pi epsilon naught q over r2. Apply principle of superposition at these values and you will get q over 4 pi epsilon naught 1 over r2 minus 1 over r1. Now you see here, we don't know the value of R1 and R2. We have just assumed. So we have to convert this R1 value in terms of dipole length L and known value R. Now you see here, draw perpendicular from A at point C on OB line which is produced backward. Okay. Similarly, draw perpendicular from point P at D. Okay. Now you see here, what is R1? R1 is AP. But from this diagram, it is approximately equal to CP. What is CP? CP is OC plus OP. Okay. So what is OC? From right angle triangle AOC. OC divided by AO is cos theta. Why cos theta? Because this is theta and in front of theta is perpendicular. So this is base. So base over hypotenuse. OC divided by AO is cos theta. What is OC? It is AO cos theta. What is AO? It is L cos theta. Okay. So what is the value? L cos theta plus what is OP? R. Okay. Similarly for R2, R2 is BP, which is approximately equal to dp. Okay, and dp is op minus od. What is op? It's r. And what is od? From right angle triangle odb, it will be l cos theta. Okay, so r1 is r plus l cos theta and r2 is r minus l cos theta. Substitute these values in this equation, equation number 1. We take the LCM, r minus l cos theta, r plus l cos theta, that is a minus b, and a plus b is a square minus b square. So here a is r and b is l cos theta. Now cross multiply, we get r cancels out with r and we get 2l cos theta. Now combine q into 2l. What is q into 2l? It is dipole moment p. The result is p cos theta divided by 4 pi epsilon naught r square minus l square cos square theta. But if point P is very far away from the center of the dipole, means r is very greater than L, then L can be neglected. So if we put this quantity as 0, what we will get? P cos theta divided by 4 pi epsilon naught r square. So this is the value of potential at point P. And the case r is very greater than L. This is the case of short dipole. Short dipole. Okay. Now this P cos theta, V equal to P cos theta divided by 4 pi epsilon naught r square. This P cos theta can be written as, P cos theta, P vector dot r cap, because cos theta comes in the dot product. So when we open this, magnitude of P vector, magnitude of unit vector cos theta. Magnitude of P vector will be P, but magnitude of unit vector is always 1. So it will be P cos theta. Okay. And r naught is the unit vector along OP. So this is the final result. Okay. And you see from here, electric potential is scalar quantity because it is the dot product of P dot r cap. Okay. Now special cases, if point P lies on the axial line. Suppose this is minus q, this is plus q, and point P lies here on the axial line. Then theta will be 0, cos 0 will be 1, and the result is P over 4 pi epsilon naught r square. That is B is inversely proportional to r square. And if point P lies on equatorial line, then theta will be 90 degree and cos 90 will be 0. So potential will be 0 on the equatorial line. Okay. Now you see the variation with axial line and equatorial line for potential. You see for equatorial line at every point the value of potential is 0. But on axial line value goes on decreasing. You see here V divided by 4. If R is 2 unit, then it will be R square divided by 4. If R is 3 unit, then it will be V divided by 9. Means with the increasing value of R, the value of potential goes on decreasing. Now what is the difference between electric potential due to point charge and due to a dipole? You know, for point charge we have V equal to 1 over 4 pi epsilon naught Q divided by R. Okay. And for dipole we have V equal to P cos theta divided by 4 pi epsilon naught R square. So means here due to isolated point charge V is inversely proportional to R, but in dipole V is inversely proportional to R square. And number 2, electric potential due to isolated point charge is directly proportional to charge. It depends upon charge, and electric potential due to depends upon source charge. Point to be noted, this is source charge, okay, not test charge. But the electric potential due to dipole depends upon P, that is dipole moment. Electric potential due to isolated charge has same value because it is spherically symmetric. Spherically symmetric. Okay. But electric potential due to dipole has zero value at all the points lying on equatorial line, and while on axial line the value of electric potential goes on decreasing with increase in value of distance. Okay. So this was about today's lecture. Thank you very much. If you want PDF notes, you can tell me in comment section or you can follow me on my Telegram channel. Please like this video and don't forget to share and subscribe. Stay happy, stay healthy.